In mechanics of rigid bodies, today we are going to see the second basic fundamentals. Actually, in this basic fundamental video, we will learn about two reference systems, or you can say we will learn about two reference frames, which are known as body reference system or body reference frame and space reference system or space reference frame. Actually, these two reference frames are used in discussing the motion of a rigid body. So, first of all, we have to know what are these two reference frames and how we can transform the coordinates of a point if you know it in one particular frame in another frame. Okay. We will also see if a vector is known. When you say vector is known, it means the coordinates of the the components of the vector is known in a particular frame. Then how we can find the components of that very vector in another reference frame. So such transformation equations will be also dealt in this particular lecture. Okay. Actually, when you say a body coordinate system, what does it mean? Actually, a body coordinate system means a coordinate system or a reference frame which is fixed in the rigid body. Okay. And the coordinate axes of this reference frame are known as body set of axes. As you can see in this figure, I have considered that this B is a rigid body, okay, and a reference system marked by S prime has been shown here, whose coordinate axes are OX prime, OY prime, and O dash prime, O dash X dash prime, O dash Y dash, and O dash Z dash. These are the coordinate axes of this particular frame. And this frame is attached or fixed in the rigid body B. So this X prime, Y prime, Z prime is actually a body set of body coordinate system or the body reference system. Okay. On the other hand, you can see the figure. I have marked another reference frame by S whose coordinate axes are OX, OY, and OZ. Okay. And this is not attached with the rigid body B, but it is fixed in a space. So this reference frame S, which is fixed in a space, that is called a space reference system or a space coordinate system or a space reference frame. Okay. And its coordinate axes are OX, OY, and OZ. Okay. Now, the origin of the body set of body reference frame S dash has been taken at the point O prime. And generally, or you can say in general, the origin of the body coordinate system is taken at the center of mass of the rigid body. So I have marked here in this figure that this point O dash is actually the center of mass of this rigid body. Okay. And where the origin of this body reference system lies. Okay. I have also marked by this dashed line the coordinate axes parallel to the space set of coordinate axes. Okay. Clearly, three coordinates are required to specify the origin O dash of this body set of axes relative to the origin O of the space reference system. So you can see I have marked that this X, Y, and Z, these are the coordinates of origin of body coordinate system with respect to the origin O of the space coordinate system, and the line joining O and O dashed represents the position vector this capital R of this origin O dashed relative to O. Okay. Now since the position coordinates of O dashed with respect to S or with respect to O is x, y, z, so you can easily say that this vector R will be equal to xi plus yj plus zk. Okay. Here actually I, j, k, these are the unit vectors along x-axis. I is the unit vector along x-axis, j is the unit vector along y-axis, and k is the unit vector along z-axis. Okay. So in this way you can represent the unit vector along x prime direction, which is I prime. Okay. Along y prime direction, this is j prime, and along z prime direction, this is k prime. These are the unit vectors along the coordinate axis of body set of coordinate axis. Okay. In fact, for the general motion of the rigid body, the orientation of the body set of axes x prime, y prime, z prime is described by three angles relative to a coordinate system with common origin at O dashed, as you can see, and axes parallel to the space set of axes x, y, z. Okay. And therefore you can say that three coordinates of the origin O dash, that is x, y, z, and the three angles which I have shown here in this figure, you can see the three angles theta x, theta y, and theta z. These are the angles made by x dashed with x, y dashed with y, and z dashed with z. Actually these three angles are also taken as the coordinates to specify the motion of the rigid body. So as a whole you can say that for dealing with the motion of the rigid body, we have to know the 6 independent coordinates or 6 independent variables. And that 6 independent variables are what? 3 are x, y, and z, which are actually the coordinates of the center of mass of the body relative to the origin of the space coordinate system. Okay. And other 3 are these 3 angles, theta x, theta y, and theta z, which actually measures the orientation of the coordinate axis of the body body reference system relative to the coordinate axis of the space system. Okay. So as a whole there are 6 quantities x, y, z, which are actually the position coordinate of the center of mass or the origin of the body coordinate system. Okay. And the 3 angles which measures the orientation of its axis, these are theta x, theta y, and theta z. So all these 6 quantities are needed for the complete specification of the configuration of the rigid body in motion at any instant of time. Okay. Actually, for convenience, first of all, we consider the origins of the space set of axes and the body set of axes to be same, and that is at O, as you can see in this figure. Okay. Actually, in order to specify the orientation of the body set of axes, we may use the direction cosines of body set of axes x prime, y prime, z prime relative to the space set of axes x, y, z. Okay. And as I have told you, we mark that I hat is the unit vector along x-axis, which is the axis of a space coordinate system. Okay. J is the unit vector along y-axis and k is the unit vector along z-axis, and these are the axes of a space coordinate system. Okay, and similarly the unit vectors along the body coordinate axis of body coordinate system, that is along x dash axis, y dash axis and z dash axis, we consider that the unit vectors are I hat prime, j hat prime and k hat prime. We consider it. Okay. Now for knowing the transformation equation from one coordinate system to another of any position of a vector or the coordinates of a point, first of all we will see how we can define the direction cosines of the three axes of body set of body coordinate system relative to the space coordinate system. And for this we consider that this alpha 1, alpha 2 and alpha 3, these are the direction cosines of x dashed axis. What does it mean? It means you can say that cos alpha 1 sorry, not cos alpha 1 but the cosine of the angle made by x dashed axis with x axis is alpha 1, and cosine of the angle made by x dashed axis with y axis is alpha 2, and cosine of the angle made by x dashed axis with z axis is alpha 3. Then how these direction cosines alpha 1, alpha 2 and alpha 3 of x dashed axis, or you can say these are the direction cosines of unit vectors I prime with respect to x, y, z will be defined. You can see. You know alpha 1 is what? This is direction cosine of x dashed axis with respect to the x axis. Okay, and if the angle between x dashed axis and x axis, which I have marked here by this angle theta x, then this alpha 1 is simply cosine of theta x. This is called direction cosine. Okay, and this is needed for knowing the orientation of the axis of body set of coordinate system. Okay, and this is also written in this manner. This is cosine of x prime comma x. When you write x prime comma x, that represents angle between x prime and x. Okay, but you know the unit vector along x prime direction is I prime. Okay, and the unit vector along x axis is I. So this can equivalently written as cosine of I prime comma I. It means this is cosine of the angle between I prime vector and I vector. Okay, and what will be this? This will be equal to I prime dot I. How you can say that this is I prime dot I? If you will evaluate I prime dot I, what will be your result? According to the definition of a scalar product, you know this will be mod of I prime times mod of I times cos angle between I prime and I. And if you have assumed it is theta x, then this will be cos theta x. But you know I prime and I both are unit vectors. So this will be 1 times 1 into cos theta x. So this is simply equal to cos theta x. And you know this theta x is also written by this symbol x prime comma x or I prime comma I. Okay, so it is possible to write down this direction cosine alpha 1 by the scalar product of I prime with I. Okay, actually in the similar manner, when you will define the direction cosine alpha 2 of x dashed axis with respect to y. It means what will be the cosine of the angle made by x dashed axis with y axis. That is alpha 2, which is cosine of x prime comma y. That can be also written as cosine of I prime comma j. And in the similar manner, this can be written as I prime dot j. You can check it. Okay. And alpha 3, which is direction cosine of x dashed axis with respect to z. That will be simply cosine of angle between x dashed axis and z axis. So it is written as cosine of x prime comma z, or this can be written as cosine of I prime comma k. Okay, and that will be equal to I prime dot k. Okay, so in this way we have defined the direction cosine of x prime axis with respect to the three axes of a space coordinate system. Okay, actually now you know, if you know the direction cosine of a unit vector, then that unit vector can be expressed in terms of these direction cosines. So the unit vector I dashed, this alpha 1, alpha 2, alpha 3 are what? These are the direction cosines of unit vector I dashed. Okay, and so I dashed can be written as alpha 1i plus alpha 2j plus alpha 3k. Okay, and as you can see, instead of alpha 1 we can also write I dash dot I. So this may be written as I dash dot I times I plus I dash dot j times j plus I dash dot k times k. Okay, so in this way we have expressed the unit vector I dashed in terms of ijk, and in this way we know the orientation of I dashed vector, or you can say the x dashed axis. Okay, actually on the same line you can also express the other two unit vectors j prime and k prime in terms of their direction cosines with respect to x, y, z axis. So if you consider that beta 1, beta 2 and beta 3, these are the direction cosines of y dashed axis, or you can say j dashed unit vector with respect to x, y, z axis. Okay, and gamma 1, gamma 2 and gamma 3, these are the direction cosines of z dashed axis or k dashed unit vector with respect to x, y, z axis. Then on the same line you can write that j dashed will be equal to beta 1i plus beta 2j plus beta 3k, and k dashed will be equal to gamma 1i plus gamma 2j plus gamma 3k. Okay, so how we can express the unit vectors I dashed, j dashed and k dashed, which are actually the unit vectors along the axis of body coordinate system in terms of their direction cosines with respect to the axis of a space coordinate system, I think you have learned. Okay, is it clear? So among these three equations where you have expressed I dash, j dashed and k dashed in terms of their direction cosines with respect to the space coordinate axis of a space coordinate system, you can see there are actually 9 direction cosines. 3 are alphas, 3 are betas and 3 are gammas. Okay, actually all these 9 directions cosines specify the orientation of x dashed, y dashed and z dashed axis with respect to x, y, z, which I have told you earlier. Actually these direction cosines measure the orientation, how the axes of body coordinate system are oriented with respect to the axis of space coordinate system that is determined by these 9 direction cosines. Okay. Now, as I have told you earlier that the prime aim of this lecture is to know about the transformation equations. When you say transformation equation, what does it mean? It means you have to find a relation between the coordinates of a point in frame S and in frame S prime. It means if you know coordinate of a point in frame S, you will be able to find the coordinates of same point in another frame S dashed. Okay. And the equation which relates the coordinates of a point in two coordinate system, that is called transformation equation. Okay. And for this, let us see the figure. I have shown here that there is a point P, and this point may be inside the body or may be outside of the body. Okay. And with respect to the common origin, when you say common origin, that means origin of the space coordinate system and body's coordinate system both are same, and that is at O. With respect to it, the position vector of this point P is R. Okay. But as the orientation of both of the coordinate axes of both of the coordinate system are different, so definitely even the position vector of point P is same in both coordinate system, the position coordinates will be different. So I have marked here that these x, y, z, these are the position coordinates of point P in frame S, and x prime, y prime and z prime are the coordinates of the same point P in frame S dashed. Now our aim is to find x prime, y prime, z prime if we know x, y, z. It means if x, y and z are known, how we can express x prime, y prime and z prime in terms of x, y, z. And converse is also true. You can also express x, y, z in terms of x prime, y prime and z prime. Actually, those equations are called transformation equations. So now let us try to find x prime, y prime, z prime in terms of x, y, z. How we can find it? Let us see. You can see R, this is position vector of point P with respect to the origin O, which is a common origin, that is origin of both of the frame S and S prime. So if you will express this vector R in terms of its components in frame S, then R will be expressed as xi plus yj plus zk. Okay, it is okay. And if the same vector R is expressed in terms of their components but in frame S prime, then what will be that? Then R will be equal to x prime I prime plus y prime j prime plus z prime k prime. Okay, it is clear. Now, how we can find x prime? You know, if you want to find the x component of a vector, okay, what you have to do? You have to do we have to find the scalar product of the vector with the unit vector in x direction. Okay, so here x prime is actually the x component of vector R in frame S dashed. Okay, and in frame S dashed, the unit vector along x-axis is I prime. So R dot I prime, that is simply equal to x prime. And you can check it from here. If you will actually evaluate R dot I hat, what will be the result? You can see R is equal to this much, and you have to take a scalar product with I dot. So this will be x hat, x prime, I hat prime dot I prime, okay, plus y prime I prime dot j prime, okay, and plus z prime I prime dot k prime. But you know, I dashed, j dashed and k dashed, these are orthogonal unit vectors. And so the angle between any two of these unit vectors is equal to 90 degree. So I dash dot I dash, this is equal to 1. But I dash dot j dash, I dash dot k dash, both are 0. So this will be simply equal to x prime. Okay. So I think you have understand how we can write x dashed equal to r dot I dashed. Okay. But r, you know, in frame S is given by this expression. This is xi plus yj plus zk. And I dashed, you have just learnt earlier that I dashed is equal to this much. This is alpha 1i plus alpha 2j plus alpha 3k, where alpha 1, alpha 2, alpha 3, you know, these are actually the direction cosines of x dashed direction or x dashed axis with respect to the x, y and z axis respectively. So at the place of I dashed you will write this much. Okay. Now in a scalar product, again you know I, j, k are orthogonal unit vectors, so I dot I, j dot j, k dot k will be 1. But whenever we will take the scalar product of I with other vectors j and k, or j with other vectors I and k with other vectors I and j, all will be 0. So after taking the scalar product, we will get x prime equal to alpha 1x plus alpha 2y plus alpha 3z. Okay? And in the similar manner, you can obtain the value of y prime, and you can say this will be what? This will be beta 1x plus beta 2y plus beta 3z. And similarly, this z prime is equal to gamma 1x plus gamma 2y plus gamma 3z. So now see this equation 4. What you are seeing here. From equation 4, it is easy to find x prime, y prime, z prime. That is the position coordinates of point P with respect to frame S prime if we know x, y and z. It means if you know the coordinate of point P relative to the space coordinate system S, then you can easily find the coordinates of same point with respect to the body coordinate system if you know the 9 direction cosines. And among those 9 direction cosines, 3 are of x dashed axis with respect to x, y, z, 3 are of y dashed axis with respect to x, y, z, and 3 are of z dashed axis with respect to x, y, z. Okay. So this is the transformation equation. Okay. Later on, we will also see in the similar manner we can express x, y, z in terms of x prime, y prime and z prime. Okay. But before that, now let us consider in general there is a vector A. Okay. A is any vector. And this vector, when expressed in frame S in terms of its rectangular components, which are actually ax, ay and az in frame S, then you know A can be written as axi plus ayj plus azk. But if the x, y and z component of the same vector in frame S dashed are ax dashed, ay dashed and az dashed, then A can be expressed as ax dashed I dashed plus ay dashed j dashed plus az dashed k dashed. You can see. In this way, we can express the vector A in terms of their components in the two coordinate system. Actually, as the components x, y, z and x prime, y prime, z prime of position vector R are related together, In the similar manner, on the same line, you can relate the components of vector A in one coordinate system with the components of same vector A in another coordinate system. It means if you know Ax, Ay and Az, you can find the value of Ax prime, Ay prime and Az prime in the same manner. Okay. So you can see if our aim is to find Ax prime, which is actually the x component of vector A relative to O dash x dash axis, that is x axis of the body coordinate system, then you know this can be expressed as A dot I dashed. Okay. And A dot I dash, that will be simply equal to alpha 1 Ax plus alpha 2 Ay plus alpha 3 Az. Here I have again assumed that these alpha 1, alpha 2, alpha 3, these are the direction cosines of this x dashed axis with respect to the x, y and z axis. Okay. And in the similar manner, Ay dashed will be equal to A dot J dashed, and that is expressed as beta 1 Ax plus beta 2 Ay plus beta 3 Az. And similarly, Az dashed will be equal to A dot K dashed, and that is equal to gamma 1 Ax plus gamma 2 Ay plus gamma 3 Az. You can check that equation 5 and equation 4 are completely identical. Okay. So I have told you that we can express the components of a vector in one coordinate system in terms of its components in another coordinate system on the basis of this equation 4. Okay. In the similar manner. But I have told you that inverse transformations are also possible. Okay. Till now we have expressed the components of position vector or components of an arbitrary vector A in S dashed frame in terms of their components in S frame. Now we can do the same algebra in reverse manner. Okay. So if now you want to express unit vector I in terms of I dash, J dash and K dash, then you have only to replace I by I prime and I prime by A. You can see I have expressed here that I prime is equal to this much. So if your aim is now to find I, you have to replace I by I prime and I prime by I. You will get the result. So in this way we can obtain the inverse of all these equations. So I prime can be written as I dot I prime times I prime plus I dot J prime times J prime plus I dot K prime times K prime. Okay. And similarly, I will be written as alpha 1 I dashed plus alpha 2 J dashed plus alpha 3 K dashed. J will be equal to beta 1 I dashed plus beta 2 J dashed plus beta 3 K dashed. And K will be equal to gamma 1 I dashed plus gamma 2 J dashed plus gamma 3 K dashed. Okay. In the similar manner, we can obtain these inverse relations. Okay. And if now you will express X, Y and Z, which are actually the position coordinate of a point P in frame S, in terms of the position coordinates X prime, Y prime, Z prime of the same point in frame S dashed, you can use the similar result which you have actually written in this equation 4. Only you have to replace X prime, Y prime, Z prime by X, Y, Z and X, Y, Z by X prime, Y prime, Z prime. Only you have to invert. Okay. So you can see I have written here X is equal to alpha 1 X prime. Here there was X and X has been replaced by X prime. Here in LHS there was X prime which is replaced by X. and the second term will be alpha 2y prime plus alpha 3z prime. Okay, and in the similar manner you can express the result for y and z too. Similarly, for an arbitrary or a general vector A, if your aim is to express its components ax, ay, az in S frame in terms of the components ax prime, ay prime and az prime in frame S dash, then the result similar to this will hold. What we will do for getting those results? Only you have to change the primed quantities by unprimed quantities and the unprimed quantities by primed quantities. Only you have to do. So you can see this ax can be written as alpha 1 ax dash plus alpha 2 ay dash plus alpha 3 az dash. Similarly, ay will be equal to beta 1 ax dash plus beta 2 ay dash plus beta 3 az dash, and similar result will hold for az. Okay. So now you can see actually these 9 direction cosines, alpha, 3 alphas, 3 betas and 3 gammas, okay, are not all independent, and the relations between them arise because the unit vector in a coordinate system are orthogonal to each other with unit magnitude. And if we consider unit vector I prime, j prime, k prime in frame S prime, then you know I dashed dot I dashed, what will be equal to it? This is equal to 1. And this will be equal to alpha 1 square plus alpha 2 square plus alpha 3 square. You know, you have definitely studied in your course on vector algebra that the sum of the square of 3 direction cosines is always equal to 1. So I dashed dot I dashed, this is equal to 1, and that is equal to the sum of the square of all the 3 alphas. Similarly, j dash dot j dash, that will be also equal to 1, and that is equal to beta 1 square plus beta 2 square plus beta 3 square. And similarly, k dash dot k dash, that is also equal to 1, and that is equal to gamma 1 square plus gamma 2 square plus gamma 3 square. But since these unit vectors are orthogonal, so when you will take the scalar product of I dashed with j dashed, that will be equal to 0, because angle between I dashed and j dashed is 90 degree. So this scalar product will be 0. And I dash dot j dashed, what will be this? You have defined I dashed and j dashed earlier. You can see I dashed is this much and j dashed is this much. And when you will take the scalar product, okay, then that will be alpha 1 beta 1 plus alpha 2 beta 2, you can see, and alpha 3 beta 3. So this is equal to alpha 1 beta 1 plus alpha 2 beta 2 plus alpha 3 beta 3. Okay. Similarly, j dash dot k dash, that is also equal to 0, and that will be equal to beta 1 gamma 1 beta 2 gamma 2 plus beta 3. You can check. And k dash dot I dash, this is also 0, and that will be equal to this much. So actually you can see here there are actually 9 relations from A to F. Okay, and these relations in direction cosines are so not 9 but 6. There are 6 A to F. There are 6 relations. Okay, and actually these 6 relations actually reduce the number 9, which is total number of direction cosines, to 3 independent direction cosines. Okay, which correspond to 3 degrees of freedom. Okay, the sixth relation reduced the number 9 to 3 independent direction cosines, and these 3 independent direction cosines are actually the 3 degrees of freedom, and this 3 degree of freedom is needed to specify the rotation about the common origin. Okay, so these 3 direction cosines, which actually represent 3 degree of freedom, that represents the 3 rotations of the rigid body about the common origin O. Okay, so we cannot take the 9 direction cosines as generalized coordinates. You can't take this 9 direction cosines as generalized coordinate to set up the Lagrangian or equation of motion of the rigid body, because they are not all independent, but they are dependent on one another. So you have only 3 degrees of freedom, and you have to choose only 3 angle of rotation to write down the Lagrangian or the equations of motion of a rigid body. So I have mentioned it here. You can see, in order to have 3 generalized coordinates corresponding to 3 degrees of freedom, we need a set of 3 independent functions of the direction cosines. Okay, 3 independent functions of the direction cosines. Actually, a number of such sets of 3 generalized coordinates have been described in the literature, but the most common and important ones are Euler's angles. So actually, in describing the motion of a rigid body, the most convenient, the most popular, and the widely used sets of 3 angles of rotation which are used as generalized coordinates, those angles are actually called Euler's angles. Okay. So what are these Euler's angles, how these are generated, and how it is very helpful in discussing the motion of a rigid body, we will learn in our next coming lecture. Okay. So next coming lecture will be regarding the Euler's angles. Okay. So I think in today's lecture we have discussed a very simple basic fact for discussing the mechanics of rigid body. Now after these 2 basic lectures, we will start the real concept of the mechanics of rigid body in our forthcoming lecture, and the first lecture will be on Euler's angles, which is a most important concept and most important generalized coordinate to discuss the motion of a rigid body. Okay, thank you very much.